In this video, what I'm going to do is I'm going to describe the laws of electromagnetism. This is going to be sort of a review of what we've been discussing so far up to this point in the semester, from the beginning of the semester to this point right now. And what we've learned is we've learned four very important laws. The first is Gauss's law. The second is Gauss's law of magnetism. Then we learned about Faraday's law, and then Maxwell's law. So I'm going to do a quick little review on each one of these laws. First one is Gauss's law. And Gauss's law states the sum of the electric field times the area is equal to the charge divided by the permittivity of free space. And what this does is this relates the electric field to a charge distribution which forms an electric flux. Remember, electric flux is the field lines going out of a particular surface. The next one was Gauss's law of magnetism. Gauss's law of magnetism. And this is the sum of the magnetic field, oops, not A, I just said that, times the area is equal to 0. And what this says, it says that the net magnetic flux through a closed surface is going to be 0. What this law does is it says that a magnet has to be a dipole. You cannot have a monopole magnet. A monopole magnet will not exist. You have to have a dipole, because according to Gauss's law of magnetism, if you have a closed surface, the number of magnetic field lines that leave that surface equals the number of magnetic field lines that come into that surface. And so that's Gauss's law of magnetism. Now, if you had a monopole, then those magnetic field lines would just go out and they would never return back to the South Pole. So for instance, we always draw magnetic field lines going from the North Pole to the South Pole. If you had a monopole and you had to just say a north magnet, which does not exist, then the field lines would simply leave that magnet and would never return. Or if you had a South Pole magnet only, the magnetic field lines would just come into that South Pole and you wouldn't know where they actually originate from. The next one we're going to be discussing is Faraday's law. And Faraday's law is the sum of the electric field times a length is equal to a change in the magnetic flux with respect to time. And so what it says is that an electric field is formed by a changing magnetic flux. Let me repeat that. An electric field is formed by a changing magnetic flux. And the electromotive force is the sum of the electric field around a closed path. Now that will equal the rate of change in the magnetic flux through that closed surface with respect to time. So let me repeat this. An electric field is formed by a changing magnetic field. And then the last one I'll be discussing now is Maxwell's law. So Maxwell's law. And that is the sum of the magnetic field times a closed loop or a closed surface is equal to mu naught I plus ID, where this is going to be the permeability of free space. Permittivity of free space. This is the current and this is the displacement current. And what this says is that a changing electric field or electric current can generate a magnetic field. So if you have a changing electric current, what you can get is what will be generated is going to be a magnetic field. Now, what Maxwell did, and this is the beautiful thing about Maxwell, there are scientists and then there are scientists. Maxwell is clearly in the latter group, because what he did is he combined all four of these laws, unified them, and showed that an electric field and the magnetic field can support a wave that travels through space. So let me repeat that. What Maxwell did was he unified these four laws, showed that the electric field and the magnetic field can support a wave that travels through space. Now, if it's a wave that travels through space, then that wave must have some kind of speed. So what he showed was he showed that the velocity of the wave is equal to 1 over the square root of the permeability of free space times the permittivity of free space. So he showed that the speed of that wave, the velocity of that wave, is equal to the inverse of the square root of the permittivity of free space times the permeability of free space. And mu naught is going to be equal to 4 pi times 10 to the minus 7th Newton per ampere squared. Epsilon naught is equal to 8.854, keep forgetting that, 2 times 10 to the negative 12 coulombs squared over a Newton meter. You plug these terms into this expression, you find out that the velocity of the wave is equal to 2.9979 times 10 to the 8th meters per second. That number should look awfully familiar in that we typically round this to 3 times 10 to the 8th meters per second, which is the speed of light. So therefore, this expression right here is equal to c, the speed of light. And what this shows us is that light really is an electromagnetic wave that happens to travel through space. And that is what Maxwell showed us. He showed us that, hey, this is what light is. It is an electromagnetic wave that travels at 2.9979 times 10 to the 8th meters per second, or 3 times 10 to the 8th meters per second, through a vacuum or through space. Now, what we're going to be discussing next will be about light.